By way of introduction, one of our team members is not here, Miguel. He had a family emergency. Omar is from our financial services division, and I work in our national advisory division. All right, so why are graphs getting popular? So if the graph is a data fabric and I can store all my data as an in-memory object, then really what I need is a lot of memory. And one of the major drivers of the adoption of graphs for enterprise workloads is the fact that memory and also compute are just getting cheaper and cheaper and cheaper. Let's go to the next slide. And so last year, I guess it was 2 years ago now, AWS started releasing virtual machines that had 4 terabytes of memory on them. And this year, if we go to the next slide, Microsoft on Azure is releasing machines that will be up to 12 terabytes of memory, and we were actually just looking at some of their 6 terabyte VMs recently. So what this really means is that you can actually take a huge amount of data and stick it on a single virtual machine. What are the benefits of that? Well, if you think about a scale-up paradigm versus a scale-out paradigm, when you scale up, you're actually getting the fastest possible I/O. Scale out, if I'm using data distributed over a bunch of commodity servers, my main bottleneck is actually network speed. So it's actually a better solution if I can just get really big VMs and stick my data on them. And I predict that, within the next 5 years, you're going to start to see, 100 terabyte machines, and potentially maybe within the decade, petabyte scale VMs. I mean, there's this huge hardware revolution that's going on right now. And graphs are, particularly in-memory graphs like Neo4j, are perfectly positioned to take advantage of what's happening. Let's go to the next slide. So what are graphs? Nodes, relationships. And if you look around, if you think about your business, there's lots of different kinds of graphs that are out there. So anything that looks like a complex network is a graph that has dependencies. Anything that has complex processes and hierarchy associated to it. So here I have a ship. I have containers. In those containers are boxes. Those containers are going to get loaded on trucks, and they're going to go to cities. And in those cities are warehouses. From those warehouses, they go to stores, and so forth. Great graph problem. Anything involving componentry. So we saw Preston's talk earlier on total cost visibility, right? All of the component hierarchies. So there's a number of graphs that are out there around components. These are typically called digital twins. And so you can literally have, in a graph database, a digital representation of every single major asset that you have and all of its specific components with each of the serial numbers of every single one of those components, all tied together. And of course, every single SQL database is a graph. The very first thing that you do when you design a data warehouse or a database is you produce your concept diagram. And that concept diagram is, in fact, a graph. And so if you have any kind of structured data laying around in a bunch of different SQL databases, and most companies will have hundreds, if not thousands, of SQL databases, you can ingest all of those databases into your graph. You can bring over the relationships and instantiate those in the graph. So with that, I'll turn it over to Omar, and we'll take a deep dive into some financial network analysis. And what I will point out is a lot of the graphs that you've been seeing so far are detailed node relationship graphs. We're going to be talking about subgraphs and how subgraphs fit into larger scale macro graphs. And so if at any point you need a reminder on what exactly we're talking about here, feel free to chime in and say, okay, guys, I'm not following, and we'll break it down for you.
Yeah, thanks, Michael. So there's a number of graph use cases from an analytics perspective that makes graphs very complementary to how you would already perform some analytics that exist, right? So recommendation engines. Anyone familiar with collaborative filtering? or how recommendation engines work and recommend products or recommend most similar persons, right? Within a graph, collaborative filtering, the mathematical construct of it is implicitly built in because all your customers will be linked together by the products they've already bought. So that mathematical operation doesn't need to happen when you try and do recommendation engines through a graph. Supply chain network optimization. This is a network. A graph is a network, right? So if you put your supply chain in there, it's like that. Fraud networks, various different fraud circles, et cetera. Community detection, social network analysis, and then what we'll talk about is anomaly detection. So background, as Michael mentioned, we started on this about a year ago with a financial service client of ours, and the problem statement was, right, so AML, or anti-money laundering, is currently, it's done as a very rule-based type system. But when you really think about it, money laundering is a network problem. You're trying to understand the flow of funds, of how it goes from one intermediary to another intermediary to another intermediary. You can't really model that business problem or even that domain in a relational structure. You actually need to bring it into a network side problem and solve it as a network or a graph construct, right? And so that's where we started trying to tackle this problem. And what we're showing you now is the framework that we've been thinking about and the framework that we've kind of built and have started maturing a bit. And now we're looking into ways of utilizing this as a generalized anomaly detection framework for graphs that can be used more than just for anomaly detection, but a few other use cases, right? And when you think of anomalous behavior or anomaly detection, normally it's for something somewhat bad, in some bad connotations, right? So AML, fraud, that type of anomaly. But an anomaly can also just mean something else. It could also be an opportunity, right? So if you're a retail bank, an anomalous behavior could also just really signal a life change in one of your customers. A new job or moving to a new state means that you are now behaving differently than what you were before. And so your new behavior, if I were to look at it the lens of what I previously viewed you as, it would be somewhat anomalous, right? And so this is kind of the thinking that we've started doing is, can we utilize this framework for customer behavior? So if you've got a new job or a new house or you got married, significant changes in your behavior, these could be potential opportunities for customer growth, either offering you new products or understanding what your needs are. And obviously for transaction networks at scale, what we learned when we were looking at this from an anti-money perspective is that it's really a problem of modeling efficient flow of funds versus inefficient, right? And is efficiency in how people or institutions or accounts transfer money around, right? Is that correlated to the type of behavior that they're trying to perform? And so how do we think of this structuring as a graph problem? So the first step, obviously, everyone's really familiar, build a customer 360 database, right? So you would utilize something like Neo4j to actually get down to, okay, my customers, my accounts, their transactions, build your customer 360, solve that problem. Once you've got that, what you'll see is you've got essentially a transaction network, right? But then you've also got this concept of scale within your graph. So as you build your enterprise graph, and as Preston was also showing, it was showing the hierarchy between tanks and then the guns and the bullets, and then also up to like your troops and your battalions, et cetera. There's a whole scaling in your large knowledge graph, right? So if we start with a retail bank, at the micro level, you would probably just be looking at, say, an account. An account would have its own relative subgraph, transactions it's made, et cetera. Go up a scale, and now you've got the full customer, right? Now customers got multiple accounts, multiple transactions. They're all part of the same graph, but you can look at them at different scales. I can look at it from an account perspective and expect different behaviors. I can look at a customer perspective and expect different behaviors in different graph structures. Go in further, and now I'm looking at potentially a household, right? A husband and wife that own joint accounts, they might have some kids, et cetera. Take a little further, and now you're looking at maybe lines of businesses, et cetera. So there's a whole scaling aspect when you look at and consider your graph from an analytics perspective. And that's where you start to think, okay, how do I actually break down my graph, right? Because the question is, if I'm trying to define behavior, I have to first define what is normal behavior. And to define what is normal behavior, I have to understand, okay, what am I actually trying to understand? And so you would have to break it down into the different scales. So you can do it scales by collection of nodes. So what I previously showed you, a collection of accounts, or a collection of customers, or a collection of households, right? And these are generally defined by your business domain or domain expertise. And then there's also scaling by collection of edges. This can generally be done whether, like a time side scaling. Okay, this quarter, next quarter, or a year, or a day, or a week, right? The scaling and how you look at your graph from an analytics perspective is very important because different scales will give you completely different views. And that's how you also then, build up the analytics use case and look at it. So in our view, from a financial services perspective, you've got your account at the micro level all the way up to the firm at the macro, and it's not, there can be clustering between scales as well. So using a toy model here, right, to kind of explain what I mean by scale and then what's inside those, if you explore that, right, so on the micro level of my accounts, if I'm just focusing and performing analytics on my accounts, you'll see that my certain products will cluster together because I expect the behavior to be similar. Credit cards will behave generally the same way. Checking accounts will generally behave the same way. And so they'll be, if you were to say segment them, which most financial firms already do, they would generally cluster together into same somewhat segments. Go into the customers, similar customers that spend the same. Their graph structure, if you run them through various different graph similarity algorithms, right, depending on how you construct it, and then also just similarity and segmentation algorithms that many banks already perform, they'll cluster together as well in their own domain. Same thing with households. If you do households by income, you'll see that they segment together and cluster together. You'll see that'll happen if you're measuring just similarity from a graph structure perspective as well.
And so just to chime in here real quick, so we're going to be using these blue circles for the next set groups of slides here. And so the point, each one of those is a graph or a subgraph within a particular scale. All of those nodes can all be sitting inside the same master graph, but if you take different slices at different scale, there's a graph of accounts, there's a graph of users, there's a graph of households that can be all constructed from the same data. And so when we're talking about the blue circles, we're really talking about different levels of scale within the graph. So hang on to that concept.
Yeah, because that allows us to set the context, right? The relative context for change in one entity relative to the other entities that we expect it to be. So another toy example, right? So to show you the scaling and exactly what Michael mentioned, if we have, say, 3 accounts, one is a college student and 2 parents. In that customer scale, they appear, we're going to look at them separately. When you move up a level to the household, they all get joined into one subgraph, and we're looking at that specific subgraph, right? So this is the context under which we will then be performing our analysis and checking for, how normal is the subgraph structure here. And that kind of then gets you thinking. Okay, so they're all clearly linked, right? The 3 accounts, they're clearly linked together, and they make the bigger household subgraph. If there's a change in one scale, what is the expected change that I should see in the next scale, right? And can we actually compute that? Can we model it, right? Can I essentially model the fusion of movement from one to the next? And you should be able to, right? If, say, the household, the 2 parents decide to move to another state, but they still have the same job, same income, now they've figured out how to do remote work and move from New York to Colorado, still being paid the same, you would expect the individual customers to potentially move in their domain, right? They're now relatively wealthier, so their transactions have probably changed. And you'll notice that the household is also going to move inside its own scale as well, to be with households that are similar to them. Likewise, if the college student graduates and moves back in with the parents or gets a job.
Take note, millennials.
Yeah. you'll notice somewhat of a shift in the household as well, because one of the underlying nodes in it that makes it up has changed, and it's changing behavior. So the household's changing behavior as well. But it's not necessarily that they're going to change in the same manner, right? So change in one scale is going to impact changes in the other scales, but it's a matter of how much, right? And that's kind of one of the things we're trying to measure. Obviously, the two parents moving to Colorado has a bigger impact on the movement in the household than, say, the student graduating college, potentially. Depends.
I guess it depends on what they majored in.
Yeah. And so the idea is, can we now model this as expected change across our graph data models, right? So what I mean with graph data models is you've obviously got your massive one enterprise graph or parent graph, and then those individual blue circles we showed you would be the different graph data models or scales, right, that you would look into. And so the idea is, what are types of small changes from one data model can impact the next, right? The example I used, household movement or newfound wealth, how does that change in one data model? What's the expected change in the next? And so by framing the problem in that way, right, the similar graph data models can give us a context for dependent way of expressing the behavioral change. And so with that, we think we can compute it. But how do you actually compute that? And this is where machine learning really comes into play, because feature engineering is going to be a really hard problem for this type of thing. In here, you essentially let the data, and this, if you turn into a big data problem, you can let the machine essentially learn what are all the different expectations, right? And so expressing behavioral change is now deeply connected to expressing the structural change on similar graph data models that are supported by the same underlying graph. Right? So that just means essentially if your subgraph is changing in one graph data model, I should expect some sort of change in the other graph data models, as we've been mentioning. And then to make it a little bit more complex, obviously I haven't even brought in the time varying aspect of this yet, right? So for each graph data model, I'm also measuring the temporal aspect, and I mentioned earlier the other dimension of scale, which is time. Whether do I want to look at this from a week perspective? Do I want to look at a monthly perspective? Do I want to look at a quarterly perspective? This type is actually what requires a lot of investigative work, right? Depending on your use case, does a week make sense for financial services? Probably not. Does a month make sense? You're getting there. Probably around a quarter to 6 month time range is what scale you want to look at for customer behavior, right? It gets some of that seasonality in there between Christmas and tax season and summer. And so we've got two different things that we're looking at. One is obviously the graph data model, which is, okay, at the customer level, account level, household level, whatever scale level I think is appropriate. And then also now the sequential level, the time varying level. And this gives me context for behavioral change, because now I can monitor the changes at each graph data model through time. And so now I bring in the concept of a time sequence graph data models, right? And so this is now the actual framework. What I described just now was actually building the graph and laying out how you can start tackling this from an analytics perspective, which in of itself is also very hard, because one thing that we're trying to do here is remove a lot of the feature engineering that takes up a significant amount of time in machine learning, but there's no free lunch. All that feature engineering time spent feature engineering is now spent designing the actual graph data model, right? Because now we want to take advantage of some of the latest stuff coming out, like graph convolutional networks or other deep learning methods, because they'll essentially try and, these are very complex structures, and so we want to let the algorithm essentially learn it without giving it much of any sort of priorities. So the first thing is that intuitive edges are semantically compatible with the parent knowledge graph. All that really means is, if I'm looking at the edges and nodes in one graph data model are essentially the same thing in the other ones, right? The notion of an account is the same across everyone. The notion of a household is the same across everyone. The notion of a transaction is the same across all my models. Obeys information theory concerns about information propagation. Let's skip that for a little bit. Use unsupervised architecture. So this is what I mean by taking advantage of some of the stuff happening in deep learning and machine learning. We are trying to remove a lot of the feature engineering because there's just so much going on in trying to model human financial behavior or even modeling human behavior that we think that we should let this be a big data problem and let algorithms essentially try and learn much of this and let us know what it thinks is anomalous, right? So we're not going to try and, the architecture learns how we should be describing behavioral change, not the other way around. We don't want to make any priorities or assumptions about what we think are normal behaviors. We'll just let the data speak, right? And normal people's financial transactions are generally very easy to model. They all generally follow a very normal distribution. And then, so use the statistical distributions learned to identify outliers. The statistical distributions that we're learning are essentially the distributions of your graph, right? You as an individual and then your financial network, the accounts that you transact with, we're essentially modeling that graph through time, and we're letting the learning algorithms actually learn what are all the different types of transformations that happen at the different scales. And then we try and create outliers. So the process is, you've got your parent knowledge graph here in green. You've got your time-varying graph data models in blue again. You'll then try and essentially, you might run some memory constraints, so you'll say, okay, I'll do a time varying of, say, 6 months or so. And you try and learn a distribution on that. The main concept being that if I can build a distribution on it, can I reconstruct your graph, right? So can I reconstruct, how hard is it for an algorithm to reconstruct your financial behavior, right? And if it's very hard, it'll give me a large error. But normally, what we have found is that the error is very low in modeling most financial behavior and transactions. If I took a log, a cumulative log error, it would follow power law, which is what I would expect. One of the things that you always see in a lot of graph analytics is that graphs and networks all generally follow power laws, right? We're seeing the same thing with modeling financial transactions and financial behaviors. And so the idea then, the key takeaway is that I'll try and reconstruct the actual real transactions you've had in your transaction network. And if there is an outlier in that distribution, then that is something that can warrant potentially looking further into as an anomalous behavior. You do this a couple times, you build a couple champion models because you want to try and build different champion models for different time frames. And then the overlap in there, what I mean by that is, let's say you build one for the household, you build one for accounts, you build one for customer. And then you try and rank, okay, let's try and reconstruct the subgraphs that have happened. The overlap in the errors, those would be the ones that you really want to focus on. And that's what we tried doing for the anti-money laundering case, in which, I don't think I can speak too much about that. But so essentially the key takeaway is, financial behavior is hard to replicate in this framework because we're essentially, everything I just talked about was setting up the graph so you could let a very complex learning algorithm learn a huge variation in structural distribution. And if it can't reconstruct what you are doing, then there is something off about what you are doing. Right? So a financial behavior is hard to replicate in this framework. The more likely the behavior can be considered somewhat of an anomaly.
Yeah, so maybe I can give a little bit of a transition example because we're going to go in and look at a specific use case. So in this scenario, imagine that you're a bank and you have 100,000 accounts, and each of those accounts you've put into a graph and you've created a concept of an account month. Okay, and the account month has all of the transactions that are occurring within that account as a subgraph, and then I have a whole series of subgraphs for every month that account has been active. Then if I compute the statistics across the entire population of account months, then I'll be able to see whose transactions vary the most from month to month. And so in the case of a money laundering example, what I would expect to see is maybe massive influxes of funds coming into an account and massive outflows of funds going into that same account, but no actual change in the net value of the account. And that's what's known as pass-through money laundering. And then we can compute that not only at the account scale, but at any higher order scale. And the vast majority of accounts will basically have the same sets of transactions. Think about when you pay your bills. You basically pay the same bills every month. Now, you might buy a car every couple of years. You might buy a house once or twice in your entire lifetime. But generally speaking, your financial behavior from account month to account month transaction subgraph is going to be basically the same. So therefore, when we break it down in this kind of a framework, we can easily compute the distribution statistics and then quickly identify who are the outliers.
Yep. And the other thing I also want to add, when your financial transactions are generally meant to try and be as efficient as possible, right? If you're going to get a mortgage, you're going to go straight to the bank or a mortgage servicer. You're not going to go to an intermediary, another intermediary, and then finally to the mortgage. So if you also look at it from a network standpoint, it needs to be efficient, right? And so inefficiencies in flow of funds is also something that will turn up as anomalous. So as an example, right, this is generally, when I say scale, this could be anything from accounts to financial institutions. The middle could be the Federal Reserve, right? And they would all look very similar like this if they are efficient transaction networks.
So you think about the way a payroll drops, right? So a company pays its payroll every month, and so there's a big drop of funds into all of its employees. Those employees turn around, they pay all their bills, a bunch of retailers, right, get paid, right? It's all very direct from a centralized source of funds out to the final recipients of those funds.
And then the example of something, and this is very easy for a model to learn and replicate, right? Something like this, right, somewhat inefficient, and you've got higher connectedness than normal. This might be a little harder for a model to randomly generate based on the distribution it's learned from all your data. And so these types of changes is what our framework is trying to capture, and we're now looking into, how do we transform this to the customer behavior modeling? Not necessarily try and tag, potentially bad behavior, but maybe potentially behaviors that's signaling, hey, there's a change in someone's life or a life event. Cool. I think.
All right. And you guys are working on a paper on this, right?
Yes, eventually. Once
All right, good. Okay,
do
so
want to write
everything
this
that you've
paper.
heard today, it will be published in some form or another by our data science group, advanced analytics group in FSO. And I just wanted to close out the talk. I realize that this is a fairly abstract concept, but what it really boils down to is that your graph contains information that isn't known to any other system. When you put your data in a graph, those relationships themselves become very, very critical data points and can drive a whole new portfolio of analytics that's basically been not available to you in the past. And so this is one of the reasons why we're very excited about graphs. More generally at EY, we've done a number of very large graph projects. And this is probably a little bit of an eye strain slide here, but I'll just read these off real quickly. Most of the graphs that we've been building are in the billions of node and relationship scales. Most of them are designed to solve some type of analytical problem, as Omar has described. But some of the things that we've done recently is for a Fortune 100 tech company, we took their entire global B2B account, contact, and marketing touch data set and put that into a graph. That had about 500 million nodes in it and 2 billion relationships. For a very large footwear company, we unified every one of their e-commerce transactions with every one of their retail register transactions, including line items, and produced a graph that touched 30 million customers, combining brick and mortar with online, which is a classic marketing problem. Total product ownership across multiple channels. For a cruise line, I can actually mention this one. This is Royal Caribbean. We're in production with a recommendation engine that takes popular activities that passengers have done and recommends them to passengers. So when you go on a cruise, you can open up the mobile app. It's available on iTunes, and it'll tell you what you ought to do based on your buying behavior and other passengers that look like you. And that's a compilation of thousands of cruises worth of data. We've done some very interesting work in AML, which Omar has just reviewed. And then also recently, we did some really interesting work in the B2B space about recommending the next best event or webinar, cross-channel recommendations based on multiple types of audiences, business decision makers, developers, and CXO level titles with specific recommendations for each title. And all of these are unified by the notion that all the data that was required was sitting in multiple systems. Pulling all the data together into a graph allowed us to do deep analytics. And then with Neo4j's in-memory architecture, we can easily wire that up to digital applications and deliver an answer in typically under 200 milliseconds. So it's very powerful. And with that, we'll close out if you have any questions. Thank you.